Hi, we're going to do whiteboard problem 16.2. And we'll just read through this here. So we have a wave traveling with a speed of 100 meters per second. That's pretty darn fast. I'm going to start writing my list of knowns here. 100 meters per second. Its wave number K is 1.5 radians per meter. And then, so the first part, we want to find the wavelength and the frequency. And then we want to, in second part, draw a snapshot graph. Okay. If we know, so that's a snapshot for t equals 0. We know that the amplitude is 5 centimeters and, and y equals 5 centimeters at x equals 0. Okay, and then finally, part 3 is write the full equation. Okay, so let's go to our ladybug. Over here. I'll accidentally close it. We'll get our page. Let's see. Okay. So, all right, so the first part, let's start with the first part. We want to find, we are given K and the speed, and we have to find the wavelength and frequency. So this is what we're given. We'll get our full presentation points here. Okay, so for part 1, find, and this is, what we need to find. Okay, so for part 1, we want to find, let me do my autofocus again, sorry about that. There we go, lambda, wavelength, and the frequency. Okay, so we know we have the wave number and we have the velocity. So we'll definitely want to keep in mind, right, just commit this one to memory, that velocity for all waves is frequency times wavelength, so that's going to help us. And then the definition of K, the wave number, is 2 pi over the wavelength. Okay, so kind of how many radians it will undergo in a meter. Okay, so let's do, so again, if we start with K equals 2 pi over the wavelength, then we can swap that and solve for the wavelength as 2 pi over the wave number, K. So it's 2 pi over our wave number, 1.5 radians per meter. And I already plugged that in, so I know that that's going to give us lambda is 4.19 meters. So that's good. Okay, now that we have wavelength, we can solve for frequency using velocity is frequency times wavelength. So I want to solve for frequency. So I get frequency is velocity over wavelength. So my velocity is 100 meters per second. That was what we were given, and I just found the wavelength to be 4.19 meters. And so I get a frequency of 23.9 hertz. Right? My units, the meters cancel out, so I'm 1 over seconds. And remember, hertz is a cycle per second. So that's really fast, right? So it's saying that the wave is undergoing, almost 24 cycles in a second. That's pretty darn fast. Okay, so that finishes part 1. Let's look at part 2. Of course, light actually has super high frequency, but for kind of a mechanical wave, that would be pretty fast. Okay, so for part 2, we want to find our snapshot graph. Okay, so our general equation for the displacement, right, in the y direction as a function of x and time is an amplitude. And in this case, we're describing the wave as a sine. Sine, cosine is only different by a phase constant, right? So the full equation is the wave number times x minus omega t plus phi, which is our phase constant, right? So this tells us, how it's starting at t equals 0 and x equals 0. Okay, so we know this, right? We know that this is 0.05 meters. We got that down. We have our wave number. We were given that, 1.5 radians per second. So we need to still find omega, and we need to still find phi. So omega is the most straightforward. The relationship, omega is angular frequency, so it's 2 pi times the regular frequency, which we just found. Okay, so it's 2 pi times 23.9 hertz. And again, I calculated that already. I got 150, if we round it to 3 sig figs, radians per second. Okay, so now we need to find phi, and these initial conditions that we were given. So at t equals 0, given the amplitude is 5, y equals 5, and x equals 0. So let's sketch out what that looks like. Okay, so our amplitude is going to be 0.05 meters. Okay, and then so we know at this is going to be our x, right? Because our snapshot is just what the position looks like, x, y versus x. So it's at a t equals 0, and at x equals 0, my displacement is 5 centimeters. Okay, so that means I'm at the peak of the wave here. So this is going to look like a cosine curve then. So for cosine, right, it starts at 1, goes to 0, then goes down to -1, 0, and back up to 1. So we sketch that in. It's like an expert curve there. Okay, and then if we wanted to put in numbers, right, we know that this wavelength is 4.19 meters, right? So right here, this would be 4.19 meters, and this would be 2.085, I guess? No, 0.99, yeah, 0.95 meters, and this is 0. Okay, so that takes care of our snapshot graph. All right, and then we actually need to solve for what the phase is to get the full equation. Because everything else we have, right? We have omega now, we have k, we have a, we just need phi. Okay, so the displacement at a particular position and time is how we will figure out our phase constant. It doesn't have to be when t equals 0, but that makes it easy. And certainly when x equals 0 and t equals 0 makes it super easy. So we know that this equals 5 centimeters. And this equals, our amplitude is 5.05 meters, sorry. Okay, and then this is at t equals 0 and x equals 0, right? We're going to use this snapshot basically to solve for what phi is. So x is 0, that term goes away. T equals 0, that term goes away. So I get 0.5 meters is 0.05 meters is 0.05 meters times the sine of phi. So we divide both sides by 0.05. Okay, and so we get 1 equals sine of phi. And if we take the inverse sine or arc sine of both sides, then I get phi equals the angle whose sine is 1. And we can use our calculators or we can use our brains for this one because it works out nicely. Sorry, my dog is telling me it's time for dinner. Right, so if this is theta, our sine function starts at 0. Regular old sine goes between 1 and -1, right? Up to 1, back to 0, down to -1, and back to 0. So we can get another professional looking sine curve here. Pretty good. Okay, so the angle whose sine is 1 is right here, right? So remember, this is the full cycle takes 2 pi. So this is pi, and that's pi over 2, and this is 3 pi over 2. So right here, that's the angle whose sine is 1, so phi equals pi over 2. And I'm going to fill this in now. So we have the full wave equation. So we have our displacement in the y direction as a function of x and time is our amplitude, 0.05 meters, times sine of k, which was 1.5 radians per meter, times x, minus omega, which was 150 radians per second. Oh boy. -1 on presentation, huh? Times t, and then plus pi over 2. Sorry about that. But trying to save a sheet of paper there. Okay, so let me just show you quick. I threw a simulation to animate that so you can see what these waves look like. So on the top, we're seeing the wave oscillating, right? So it's not just a pulse like we've seen before. This is a wave that's continuous through space, that's oscillating back and forth. We are just showing you what a history graph looks like for this position, at 3 meters. So here, right, we can see kind of, from the trough, maybe quite to trough is about, 4 meters is the wavelength. This history graph is showing us how quickly a particular position in space is oscillating. It is pretty fast. Because remember we said it made like 24 cycles in a second. So if we do the inverse of that, we would get the period, which I think I calculated at some point. Yeah, it's like 0.04 seconds. Right, so we can see that here. I mean, not even 0.05 seconds. It does a complete up and down period.